developments of dynamics methods for the nuclear dynamics using quantum and trajectory-based approaches. And today I'm going to try to give like an overview of the problem of like when combining electronic structure calculations with nuclear dynamics on a problem which manifests intersystem crossing in a molecular reaction. So, so in this slide, I introduced the problem and the collaborators. So these are here Sabine Morisset and Nathalie Rougeon, and they work at the University Paris-Saclay, but at the Institut de Sciences Moléculaires d'Orsay. This is David Levergnat, who works at the Institut de Chimie Physique, like me. So a couple of years ago, Sabine and Nathalie came to us saying that they were interested in studying the collision reaction of oxygen in the triplet state with the ethylene. So at that time, we didn't have PhD students or postdocs, so we wrote a few application grants, and so we got funded, and we hired Francesco Talotta as a postdoc. So Francesco has been with us until 10 days ago. Now he's enjoying some relaxed time in Italy before starting his new position as associate professor at the University of Lorraine in Metz. So he's the main guy who did the job here, which is still, I would say, ongoing. So it's not finalized yet. So why this collision reaction? I'm not gonna deny it. The literature is full of results on this reaction, experimental and theoretical. However, I find it really intriguing from the theoretical point of view. So first of all, because despite the fact that only light elements are present, there are some configurations that the system encounters along the reaction that manifest a strong spin-orbit coupling, or at least a spin-orbit coupling that is strong enough to induce intersystem crossing. So basically an electronic transition between two electronic states of different spin multiplicity, in this case, singlet and triplets. So the theoretical studies that we found in the literature are based only on surface hopping. They consider only two electronic states, so the lowest singlet and triplets. There are some DFT calculations, but mainly the larger amount of literature is obtained by doing calculations on fitted potential energy surfaces. So they run a lot, like millions of trajectories of surface optic trajectories on these analytical, basically, potential energy surfaces. They are fitted by using different electronic structure methods depending on the part of the configuration space that they are looking at. So they use MRCI, they use KCCF, and they use Kleber cluster. So this is at least the method that I remembered. So starting from this, what we proposed to do in this project was to focus on or develop a method for on-the-fly dynamics on ab initio potential energy surfaces without the need to fit the surfaces. So here the problem was like to find an electronic structure method that was good enough to give us basically the correct energies and the electronic structure for the many reaction channels of this collision reaction, and also to use for the dynamics a different method that is not surface hopping, but that we can use to account for intersystem crossing. So now I'm going to talk about these 2 points during this presentation. So for the first part, so I'm showing here some like these are preliminary trajectory calculations. These are not published yet. This part of the project is still ongoing, but it's just some that give you an idea of what happens during this reaction. And these calculations are performed using Shark and OpenMolcast using surface hopping. So here, so in the literature, in particular, I refer to this paper here. There were 5 reaction channels that were identified that were the most probable reaction channels. These 2 here, they take place only on the triplet potential energy surfaces, and the first one with about 20%, and the second one with 6% probability at this collision energy. So these are, again, the results taken from surface hopping calculations on the fitted potential energy surfaces. So we have tried to reproduce these 2 reaction pathways by using a CASCCF and the CASPD2 method. I will give you some more information later on the details of the numerical details that for the calculations. So basically, the first thing that I would like to underline here is that we are using here 4 electronic states, so 2 singlets and 2 triplets, because as you can see, there are some configurations where, like for instance, here, the singlet and the triplets, the states are very close in energy, so there is no reason to choose one or the other for the dynamics. And so what is shown here is that this is basically what we call the entry channel. So the oxygen here approaches ethylene. This structure here, that is a triplet biradical, is formed. And this is the region where singlets and triplets come close in energy and where intersystem crossing can be observed. In this particular reaction channels, though, reaction pathways, the system remains in the triplet and it forms either this product here or this product here. Product 2 is actually what we are observing here. So here the energies now that are given, I will say more in a couple of slides, are our CASPD2 calculations. And what also I want to underline is that for this configuration here, where intersystem crossing is likely, we also observe a conical intersection between S0 and S1. And the presence of this strong coupling between these 2 singlet states, which is not taken into account in previous calculation, could actually maybe affect the dynamics, or at least the reaction times. In this other figure, instead, I'm showing to you the other 3 channels that have been identified also here by surface hopping calculations. And these are reaction channels that terminate in the singlet state. And these are the probabilities associated to these 3 products at the same collision energy as before. So this is, again, the entry channel, this is the biradical, and then here there is actually an intersystem crossing taking place, and the system ends up either here in this configuration, this is the 4th product, or here in the 3rd product. And the 5th reaction channel is not shown in this figure because it was difficult to put everything in the same figure. And so this is the spin-orbit coupling that is calculated in this region. It's not very strong, but still it's enough to induce intersystem crossing. So this is basically our study to identify, where we identified some critical configurations along these 5 reaction pathways. We have also done some studies, so everything is reported in this publication from last year, and we have also done some studies of potential energy profiles along the reaction pathways. So this is the active space used for the calculations. These are the orbitals are represented only for the oxyrane structure. So basically, when ethylene is attached to the oxygen atom, and so the curves that I'm showing here are the CASPD2 calculations, and they refer to the entry channel. Again, the oxygen here approaches the ethylene, and at this transition state configuration, there is you can see there is this little barrier that the system encounters before forming the biradical. Now in bold are the results of our CASPD2 calculations with the error compared to the results reported in this paper. And so the problem here is that we cannot do CASPT2 when we do the trajectories for the dynamics. It takes too long. And in fact, the dynamics that I showed before in the previous slide was done with CASCF. Now I want to show you the result of the CASCF for the same entry pathway. You see here the barrier is larger with CASCF. So this is something that we have observed. The barriers are overestimated. Maybe, I don't know, this is something that is well known, but as a new comer for this in this kind of calculations, I mean, I found this really surprising. And the problem is that basically we cannot do really the dynamics without tuning a little bit the results from CASCF, because in the initial dynamics, in the initial trajectories that we were running with CASCF, we were just finding basically that the oxygen bounces back and it doesn't get attached to the ethylene because the barrier is definitely too high. So this is something that we have to take into account, that we have to correct when we're going to do some more dynamics calculations. So with this approach. So this is everything that I wanted to say about the electronic structure part of the project. And then I'm going to go through the second part of the talk, where I discuss a little bit some non-adiabatic dynamics method to capture intersystem crossing in a molecular reaction in general. So first, I'm going to discuss in general the part of non-adiabatic dynamics, and then I'm going to put spin orbit coupling in the problem. So when we think about when we think about developing methods for non-adiabatic dynamics, which means coupling, the manifest coupling between electrons and nuclei beyond the Born-Oppenheimer approximation, what we should always start with is a very general equation. That is the time-dependent Schrödinger equation for the system of interacting electrons and nuclei. So here I indicate with psi the molecular wave function that depends on electronic positions and nuclear positions, and of course on time. And in parentheses here, I have the molecular Hamiltonian with the nuclear kinetic energy and the electronic Hamiltonian that contains in turn the electronic kinetic energy and the interaction potentials. So we are all aware that this equation here cannot be solved numerically exactly on nowadays computers, and therefore the idea is to use this equation to start developing approximations. There is an intermediate step that is usually done, which is to represent the molecular wave function in this form by using this what we call the Born-Huang expansion, where the molecular wave function is expanded as a linear combination over a basis set, phi. These states are the eigenstates of the electronic Hamiltonian, and they depend parametrically on the positions on the nuclei. And the coefficients of this expansion are usually called the nuclear amplitudes, because they depend only on the nuclear positions. Now, the well-known trajectory surface hopping method is developed starting with this idea in mind. There are more quantum methods, more quantum methods that have been developed over the years, and here I mentioned just some of them. The direct dynamics, variational multi-configurational Gaussians, ab initio multiple spawning, and ab initio multiple cloning. These are just some examples of trajectory-based methods that are derived from the Born-Huang ansatz. In 2010, in the group of Hardy Gross, the Max Planck Institute in Halle, in Germany, this expression for the molecular wave function, which we call exact factorization, was proposed. As you can see, it differs from the Born-Huang ansatz because it is a single product. It's not a sum of products, it's just a single product. We have here a nuclear wave function, and here we have an electronic wave function that maintains this parametric dependence on the nuclear configurations like in Born-Huang, but now this electronic state is time dependent, and this is different compared to what we had here. Starting from this exact factorization, we developed an algorithm for non-adiabatic molecular dynamics which we call the coupled trajectory mix and quantum classical, which is the algorithm that I'm going to describe to you later, and to apply to the case of intersystem crossing. There are some other methods that all collaborators from the Halle time, where I did my postdoc, or also I myself am currently developing, starting always from the exact factorization. But I will focus mainly on this CT-MQC in the next couple of slides. So now to go from this problem here to a problem where we need to account for intersystems, is just enough to add to the molecular Hamiltonian a spin orbit coupling term. Okay, so this is what I'm going to consider later on. And now we will consider the electrons labeled not only by their positions, but also by their spins. So this will be my time-dependent Schrödinger equation that I will use as reference later on. So now, before going into the details of the derivation of this coupled trajectory mixed quantum classical algorithm, I want to just stop for a second and a bit like summarize the problem that we're dealing with. So basically, to do Nonadiabatic molecular dynamics, what we need is to put together information on the electrons and information on the nuclei. From the electronic point of view, what we need and what we will need also in the new algorithm that we have developed starting from the exact factorization are, like, I would say, standard electronic structure informations, which are energies, energy gradients, Nonadiabatic couplings, and spin orbit coupling. So basically, this is the reason why. So what we do usually is to characterize the reaction that we're looking at from the quantum chemistry point of view. Using this electronic information, now we want to do molecular dynamics calculations, including the effect of excited states, by propagating a large number, as large as possible number of initial conditions with classical forces that account for all electronic states. And now these classical forces, they differ depending on the method that we're using. So when you do ultrafast, when you do AIMS, when you do surface hopping, you use different kind of forces. And this is basically the most important difference with respect to the other methods, the previous methods that we are introducing with this CT-MQC approach. Now we have seen, like this morning, a presentation about initial conditions. So here, what we need to do is basically like to make copies at time zero of our system, and then make these copies, which slightly differ have different positions and velocities, make them evolve on the potential energy surfaces, on the electronic potential energy surfaces, in order to capture the vast manifolds of reaction products that we have, like for instance here, like here in the case of this collision reaction. And I'm showing to you here just a schematic, like a cartoon of what I just said. So the curves here are the electronic energies. So they are a function of the nuclear coordinates. Every dot is a different copy of the system at time zero. Since they are different, they can move on these which are always the same potential energy curves, but they give different final answers. So now what we want to do is to propose a method that allows us to do non-adiabatic dynamics calculations, so with inclusion of spin orbit coupling and using the exact factorization as a starting point. So what we did was to insert this exact factorization form of the molecular wave function into the time-dependent Schrödinger equation, including spin orbit coupling effect. So this approach has been recently developed and is an extension of what was done by Hardy Gross a few years back. So when we do this, when we do this, we can derive from this single time-dependent Schrödinger equation for the molecular wave function. We obtain two coupled equations, one for the electronic term and one for the nuclear term. Now, in the electronic term, so you see here, in square brackets, you have the electronic Hamiltonian, that is also here. And you have the spin orbit coupling that is also here. And thanks to the exact factorization, we get this extra term that depends explicitly on the nuclear wave function, which means it depends on the solution of the equation for the nuclear dynamics. If you look at the nuclear equation, you can see here in square brackets a Hamiltonian. You have a kinetic term and a scalar potential term. In the kinetic term, there is a vector potential that depends on time. This potential scalar potential energy, it also depends on time. These two terms, A and epsilon, they depend on phi. So they depend on the solution of the first equation. So the two equations are coupled, and basically the electrons somehow during the dynamics they produce some sort of electromagnetic field that acts on the nuclei, and the nuclei evolve on this, let's say, effective potentials generated by the electrons. And the potentials depend on time because the electronic system evolves in time. Now, it's very difficult to solve these two equations like numerically exactly, so we do not want to do that. But the point is that once we have split the problem in two parts, we can develop approximations, which for me would be classical approximation for the nuclear dynamics with on this equation, and then keeping as exact as possible the electronic equation. So basically, we have to do the classical limit of the nuclear equation, introduce the concept of trajectories that evolve according to some forces, and then what we do in the electronic equation, we expand the electronic wave function on a suitable electronic representation to get from this evolution equation an evolution equation for the coefficients of this expansion. When working with spin orbit coupling, there are two possible suitable choices of electronic representation, which are called the spin adiabatic and the spin diabatic representations. If we do this, we obtain these two coupled equations, one for the evolution of the coefficients, and one is the force that evolves the trajectories. It's not important at the moment to understand everything in these equations. What only I just would like to underline is that these two terms here that we call that we define mean field terms, they are nothing more what we want to already have in an iron fast like kind of dynamics. Thanks to the exact factorization, we obtain these two coupled trajectory terms, which can be only calculated if at every time I know the positions of all the trajectories. So basically, the trajectories cannot be propagated one after the other independently, but they have to be propagated all together. And then, since I have added here the effect of the spin orbit coupling, there are these two terms that contain the matrix elements of the spin orbit coupling Hamiltonian in the basis that I chose to represent my electrons with. And we called this algorithm generalized CT-MQC. So this is an extension of the original algorithm that we proposed in 2015. Now here, since this is like new algorithm, we test it on a model system, one-dimensional system, such that we can have a comparison with exact calculations. Here and here, I'm showing results done with algorithm in the spin diabatic basis, and here I'm showing results of the dynamics done in the spin adiabatic basis, because it depends on which code basically you would like to use for the electronic structure calculation, that you have access to either the spin diabatic or the spin adiabatic information. In this case, you have eigenstate of only the electronic Hamiltonian, and here you have the eigenstates of the electronic Hamiltonian plus spin orbit coupling. So now here, this is the nuclear density that represents the exact evolution of my system when my system is prepared either here or here, and then it moves towards the right. In green, results from spin adiabatic calculations. In pink, results from spin diabatic calculations. You see, this is the histogram of the trajectories, and you see that you don't get the same results. Okay, you can observe this from the histograms of the trajectories, and you can also look at the, you can also look at the distribution of the trajectories on the potential energy curve. So you get slightly different results depending on the basis that you're using. This is because this is an approximate algorithm, it's not exact dynamics. So the results might depend on the or basically on the approximations that you do, depending on which basis you use. But if you look at the population of the two states involved in the problem, they compare very well to exact calculations in both cases. One thing that I forgot to say is that here the spin-orbit coupling is basically a sigma function like this. So it's positive here, negative here, but that's constant. And then it changes sign at r equal 8 atomic units. This is, I think, everything that I wanted to say. So we're still in the process of interfacing this new algorithm with open molcas in order to try to compare surface hopping calculations with CT-MQC calculations for the collision reaction that we wanted to study. So, but I just I cannot say more about this reaction at the moment. So just to conclude, so I think that it seems like a simple problem to treat this reaction, but I mean, if you want to use ab initio on-the-fly dynamics, it's a pretty challenging problem to treat. We have done the first part of the job by doing a multi-configurational study of the electronic structure of the system. We have developed a new algorithm for solid state dynamics, including spin-orbit coupling, but we still need to put together these two plus points, as I told you. And okay, with this I'm done, and I would like to thank you for your attention.
Thank you very much, Federica, especially for staying on time. So we have time for several questions. Yeah, Luca.
Yeah, hi. I was curious, it's more great work. I was curious about the choice of the active space in your multi-configuration part. I think it's your slide 6 or 7, if you can. Yes, because I think if you could just comment on how you chose those orbitals. Was it because of
so basically, yeah, basically the point is that there are, I mean, this molecule breaks in all directions.
Yeah.
So as you can see here, okay, so here, yes, you have an H that goes away. Actually, the most complicated one is to get this H2 that goes away. So it's basically like trial and error, and basically it took Francesco almost 1 year to just work this out in order to have, because in principle what we did, we looked into these 5 reaction pathways, and we basically studied the potential energy profiles. So when they were smooth enough to be acceptable, we accepted the active space.
Okay.
So this is basically the way the work has been done. Yeah.
All right. Great. Thanks.
Thank you.
Other questions? Okay, I have one. And since you mentioned it, the sampling of initial conditions. So I would say in general, it should be an instrumental function, so the distribution of initial conditions. And what have you done to obtain converged results in theory?
So yeah, for instance, here, what we are doing, so the point is that here we're moving a little bit in the dark because we're not experts in collision dynamics. Usually what we do, we just do some kind of like initial instantaneous excitation from ground state potential. So we use either like harmonic Wigner or some classical Boltzmann sampling at some final temperature. So in this case here, for the surface hopping trajectories that we have run, we basically did a Wigner sampling of ethylene, and then we put the oxygen, I think, at 8 angstrom distance from the center of mass of ethylene, and And we basically then we distribute it homogeneously around ethylene, and we throw it at ethylene with the collision energy that we indicated from the literature. So this is the ideas we came up with with this collision dynamics.
So essentially, it's I would say it's a homogeneous distribution. At least it sounds like this for me. Yeah. Okay. Thank you very much. So I see no further questions. So and we move on. Yes. Let's thank you.